Hello friends, welcome to my channel Easy Aviation. Here we discuss about the small short topics of the aviation, definitely the interesting one. Today's topic of discussion is atmosphere, as you can see on the screen. So atmosphere is divided into these layers. First is troposphere, stratosphere, mesosphere, thermosphere, and exosphere. So as an aviation enthusiast, you should be aware a little bit about the atmosphere, about the medium in which the aircraft fly. So I rather say these layers are not much of importance, but troposphere and stratosphere are of very important. The first one is troposphere, which goes up to 12 km from sea level. Stratosphere is from 12 km to 50 km. Mesosphere, just a little intro, mesosphere goes up to 85, thermosphere up to 690, and exosphere from 8,000 to 10,000 km. So we'll also discuss about the different parameters like temperature, density, pressure, how they vary when we go up from the sea level to the troposphere and stratosphere. So first we'll discuss about the temperature. You have definitely heard about the ISA condition. ISA is the International Standard Atmosphere. So as per ISA condition, the temperature is 288.2 degree Kelvin. This is the ISA condition. This is the temperature at sea level. At sea level. So when we are going up in the height at 11 km, that is the troposphere, the temperature reduces at a constant rate. This rate is known as the lapse rate, denoted by lambda, and this value is minus 6.5 degrees centigrade per kilometer. It is, if you convert it into feet, it's somewhere 1.98 degrees centigrade per 1,000 feet, somewhere near to that. So this is the lapse rate by which the temperature reduces. So when you find at 11 km, the temperature is reduced to 216.7 degree Kelvin. From troposphere to stratosphere, that is up to 50 km, the temperature remains constant, and from stratosphere to mesosphere again it increases. There is another lapse rate for that. So till stratosphere, if you want to, if you need to, that is the point you need to know, that the temperature reduced till troposphere by a rate of minus 6.5 degrees centigrade, and then it remains constant till the end of the stratosphere. Now coming to the pressure part. So pressure at again the ISA condition, pressure is 1.013 into 10 raised to power 5 Newton per meter square. So this is the ISA condition. This can be written as 1 bar, as 1 bar is equal to 10 to the power 5 Newton per meter square. Small conversion factor, it can also be written as 101.3 kilonewton per meter square. Also in bar is written as 1013.4 millibar. So these are the different notation you can see the pressure is mentioned in various in different books. So now how it vary with the height. So I'll take x-axis as height, and here the pressure. So at ISA so at 0 kilometer, or at sea level, rather right sea level, the pressure is pressure is this 1.013. As we go up in the height, first datum will take at 11 km, that is the end of the troposphere. So the pressure continuously reduced, and if you want to check the pressure here, the pressure is 0.227 into 10 to the power 5 Newton per meter square. So this will be the pressure. As you go up in the height, pressure again reduce. The reason is, as since Earth there is a gravitational pull, and there are particles all over in the atmosphere. So the particle here has more particles above it. So because of the pull, these particles are under more pressure, and of course the density increased. So the particles here as compared to here are under more pressure as compared to the particles here. So as we go up, the pressure and the density, they reduce. So now coming to the density part. density, I'll write rho. So density at again ISA condition, the density is 1.125 kg per meter cube, and again the curve I'll make. This is sea level, and density again follow the same curve. This is sea level, this is the density at 11 kilometer. The density reduced from 1.125 to 0.365 kg per meter cube, and again it will reduce more as we go up in the height. Explanation are already given in the previous why it happens. Next we'll go to the dynamic viscosity. Okay, viscosity is defined as the resistance to the flow of the fluid. The more viscous the fluid is, the less will be the flowability. So at ISA condition, again viscosity is 1.79 into 10 raised to power minus 5 kg per meter second, and it reduced to 1.42 into 10 raised to power minus 5 kg per second. Since viscosity is directly proportional to temperature to the power 3/4, so since the temperature is reducing as we are going up to troposphere, this is still troposphere till troposphere, temperature is reducing, so viscosity reduce, and in mu is constant in stratosphere. Okay, so this is the relation between the dynamic viscosity and the altitude. Coming to kinematic viscosity. So viscosity is kinematic viscosity is another variable, which is the ratio of the dynamic viscosity and the density. So at sea level, its value is 1.46 into 10 raised to power minus 5 meters square per second. This is ISA condition. So as we go up in the height, both dynamic viscosity and density, okay, I'll just write as we go up in height or altitude, mu also reduces and the density also reduces, but the density reduces more rapidly, so which leads the kinematic viscosity increases with altitude. Very important to note that part. And this happens both in troposphere and stratosphere. Very important, because in troposphere both are reducing, but in stratosphere dynamic viscosity is constant, but density is still reducing. So this is this is the part. So next we'll go to the next page. Next we'll go to the speed of sound, how the speed of sound behave. So speed of sound is dependent on the temperature. I'll just write the speed of sound is under root of gamma RT. So gamma is the ratio of the constant, gas constant, R is the Joule's constant, T is the temperature. So I'll just write C is proportional to the under root of temperature. So temperature, since the temperature is reduced, the speed of sound also reduces as we go up the height. Another related to this is the Mach speed, which we calculate. So Mach of an aircraft, or Mach speed of an aircraft, is the velocity by which it is moving divided by the speed of sound. So as we at a set velocity, let velocity is 500 meter per second, so the Mach value corresponding to this value is x, and if we go up Mach at 11 kilometer, this Mach value will be higher because the speed of sound will be I'll just write at velocity upon c, since it has been reduced as I've discussed here. So the Mach value corresponding to this velocity will be higher, So these are the, so here I'll sign out explaining all the various important parameters of the atmosphere and how they are varying when we go up in the altitude, or when my aircraft is going up in the altitude. So thanks a lot. Thanks to watch my video. Thank you.